All right, everyone. I hope you guys did well with your bone evals yesterday and today. This is Friday. This is the extra video or recording for the rest of the Exam 2 material. So I will see all of you on Tuesday for the normal lecture, which I will then continue on with Exam 3 material, which some of it is a continuation of bone, so a little bit of a review, which won't be bad. And then on Thursday will be Exam 2. So internet students need to sign up for the exam through Blackboard. And don't forget to make your appointment with the testing center. Remember, if you're internet and the testing center, you have from Wednesday 8 a.m. until Thursday 1 p.m. to finish the exam. Otherwise, you need to take it with us in the class. So for the in-class students or internet students taking the paper exam, it's Meyer Health Science Room 106. From 1 p.m. until 2:15 p.m. Don't forget a number 2 pencil and your student ID so that way you can fill in your student ID number. And this lecture, of course, will take you to the end of Exam 2 material. We will be finishing Chapter 5 and starting and finishing Chapter 6 today. We left off on Thursday with appendages of the skin, which includes glands, hair, and nails. So we finished glands. Now we're going to go into hair and hair follicles. And real quickly, I just want to make a comment that there were a few students who were doing some things that were a little questionable during the bone evals. And so I just want to remind everybody about academic dishonesty. If you are caught cheating, academic dishonesty goes on your record. And do you think you're going to get into any program here or anywhere else if that is on your school record? Absolutely not. So don't take the chance. Don't try to do any kind of academic dishonesty, whether it's trying to look at your phones during any eval or exams. Don't talk and whisper to other people. No wink, wink, nudge, nudging, etc. Keep it above board, everybody. Your grade is not worth being kicked out of school. Okay? So study harder instead of trying to find ways around it, and you will find that your grade will improve, and we'll go from there. So enough said. Don't do academic dishonesty. Let's do this thing. All right, so hair and hair follicles. So we have structure is mostly fused keratinocytes with the shaft, root, and bulb. So fused keratinocytes, what are keratinocytes? Those are your stratified squamous epithelial cells, correct? Yes. The shaft is what you see above. So this whole area here would be the shaft of the hair. The root is what you don't see, and the bulb is the base of the root. So you're talking about here's your root area, and your, or the bulb is down here, and then you have the root is the rest of this part right here, okay? Now, moving right along, if we talk about the medulla and the cortex, so this is terminology that you're going to hear throughout anatomy and physiology, both 227 and 228. Medulla typically means an inner area or the center of something. Cortex is typically going to mean the outer area or something that is surrounding the medullary area. So medulla is the inner core of the hair. The cortex surrounds the medulla and will end up being the bulk of the hair. The cuticle is the outermost single overlapping cell layer. So it kind of looks like scales. If you've seen like an electron micrograph picture, and then they try to tell you that you can have healthier hair if you use the right shampoo or oils or whatever, and it kind of smooths it out and gives you a nicer looking hair, the hair shaft that we see. And so the papilla is a small bit of CT that extends into the hair bulb, and it contains blood vessels and nerves. This is what will nourish your hair, if you will. And then let's talk about the hair matrix real quick. This overlies the papilla. Mitosis is what gives your hair the growth or your length of your hair, because of mitosis, it's making the hair grow longer. And then the color of your hair, like we mentioned before, is determined by your hereditary genes, which means the type of melanin in your cells is already coded to say what color the hair is going to be. So if I I'm not going to grow hair for you right this second. We're all growing our hair. But basically, if you had the surface of your hair here, or skin, sorry, here was this area. So this would be our epidermis, this would be our dermal layer. And in the dermis, you have all of that CT, right? Well, if we were to push down or cause what we could call like an invagination, then we would have the epidermis here would kind of dive down and come back up here, and your dermal layer with the dermal papilla would be here. And let's make, I said that we had a papillary area. Oh, let me fix this here and give you a better picture. All right, so if this were to kind of give us what we called a papilla there, right? So we had dermal papilla, and this is a papilla. And remember, your epidermis is constantly making more stratified squamous epithelia or keratinocytes, and so it is pushing towards the surface as it makes it. Well, not just to the surface here, but when you're inside this invagination, you're also coming in sideways as well. So you have these keratinocytes, don't forget a couple of melanocytes, and as it's pushing this direction, you kind of end up like this. And this is your hair, because we said that it's made out of mostly fused keratinocytes. So I'm just trying to show you how it would kind of grow along this direction. So coming from here, and I drew a space in there, but I want you guys to realize that it's kind of like, here's that papilla from the dermal layer, and it's like this. And so your epidermal cells, the epidermis, your stratified squamous epithelial, is filling that in, and what you see with your naked eye is the hair shaft, but it's really a bunch of fused keratinocytes. So, and then because this is all mitotically active along here, and this is where you're getting your nutrition from because the blood vessels are from the dermis, these cells end up being dead by that point on the hair shaft itself, but this is why it's going to grow in that direction and looks like it's coming out of the skin. Okay. So other things that we can talk about, the structure of the follicle itself. So it's a tube extending into the dermis. And so this is our tube that I drew here, right? This tube area that invagination. And so connective tissue root sheath is from the dermis. That'll be your outer layer. The epithelial tissue root sheath is coming from the epidermis, which will be the inner part. Then we have the erector pilae muscles. So this pulls the hair into an upright position. And so it's made out of smooth muscle. This is what gives you goosebumps. So if we look at this picture up here again, this right here was the erector pilae muscle. And so when it, I'm sorry, let's say that again. The erector pilae muscle is right here, and it's going to pull on that CT that I colored in darkly. So this is erector pilae muscle. It will tug on this when it contracts, pulling the hair shaft into a more upright position. So I'm going to erase that so that you can see it more clearly. All right. So, you know, sometimes what do we get goosebumps from? Sometimes it's that perceived thing of something behind you and about to attack you and get you. Yes, so that's why I was trying to joke and make you guys think about it a little bit. So that's your erector pilae muscle. If we talk about distribution of hair, it's over most of our body, except for just a few places. And where you have that fine body hair, we call it vellus hairs. That's your peach fuzz. So we have peach fuzz on our face, for example, right? And then we also have terminal hairs. So these are the longer hairs. They're more heavily pigmented. They're thicker also on the body. And so this would be areas like on your scalp, your actual hair on top of your head, axillary region, so in the armpit, pubic areas, so pubic hair. Pardon me, eyebrows are thick and terminal hairs, as well as facial hair, usually if you're talking about men, but even women when they have hirsutism or they're getting hairs where we don't typically see hair on women because their hormones are a little out of balance. That would also be a terminal hair as well, like the bearded lady, right? All right, so growth and replacement is cyclical, meaning that it goes in a process to it. So you could use the acronym ACT if you want, A-C-T, A for anagen, C for catagen, and T for telogen. So with anagen, this is, you could think A for active growth. So this is, most hairs are in this phase. And active growth, whenever you think growth, you're going to think mitosis. So this is mitotically active. And different areas of the body have different growth cycles, thus different hair lengths. So for example, your eyebrow hair isn't typically as long as some people's hair on top of their head, or people can grow a mustache really long and other people not so much. But this is, that growth cycle would mean like a longer growth cycle versus a shorter growth cycle would be akin to a longer length of hair versus shorter length of hair. If you talk about the catagen phase, this is where hair growth is in regression. So the hair follicle undergoes involution, or you could think of it as kind of withering, almost like a dormant phase. So it isn't dead, it hasn't died, it's just more dormant in that part of the cycle. If we talk about the telogen phase, we say this is the resting phase, kind of more like hibernation. Hair is actually being shed in the telogen phase, and this can last for a few months before the follicle would gear back up again and be ready for the anagen growth phase or active phase. So for example, hairs that are in the telogen phase, if you were to brush your hair out and you see all those hairs in the brush, so mechanical stress, so not like bad stress, but if you mechanically tug on your hair, you might feel like a couple hairs come loose, and so that means they were in the telogen phase and they can be shed at that point. And or if you were, shampooing your hair in the shower, and then after you've showered, you see some hairs on the side or on the floor of the shower that you didn't totally rinse down, same thing. They were just, mechanical stress of rubbing or pulling the hairbrush through. It's not people yanking their hair out. We're not talking about that. And now moving on to, so you can see in this picture here was your erector pili muscle, which would tug on the hair shaft and pull it into a more upright position. This is a histology view of the hair bulb. So this was the papilla that we were talking about. Here you're going to have some melanocytes, and then you have all of these keratinocytes in through this area. So you have the matrix area, you have the cortex area or medullary and cortex, right? And that's about it for the hair. Nothing too exciting, except most of us have it. If we move on to nails, another appendage of the body. So the bulk of the nail will be the nail plate, and the free edge is the most distal part. So the free edge is what we actually trim off when we cut our nails, right? The body is the visible part, and it overlays the nail bed. The root back here is embedded under the skin, and so you don't see that with the naked eye. Of the root, you have a nail matrix and a lanula. The nail matrix is the actively growing part of the nail. And so that we would say if it's actively growing, that's where it is mitotic, right? So mitosis is actively going on there. That's what causes your nail to grow. And then lunula is the half moon, is what that means. Luna for moon, right? So this is the area that appears like a half moon on your nail, and it's whitish due to the thickened area of stratum basale. And then we have our nail bed, which will be in the dermis itself. Okay, so this is what's under the nail, the pinkish area. So this makes sense, because if it would be pink, it means we have our blood vessels in the dermis, not in the epidermis, and that's what would make your nail look pinkish. So I'll erase those drawings so you can see it again clearly. And there you go. That was the nail. Oh, and then eponychium is the fold of skin that we all know as the cuticle. So the fancy word for that is eponychium. Let's see, what else do I want to tell you? That's about it. Again, nothing Too exciting. Also, okay, so the nail matrix is what are making, we said that's where mitosis is occurring, that's where the keratinocytes are, and it will grow back unless it is damaged in the nail matrix. So when we trim our nails, you see the nail grow. If you were to damage your nail out here, as long as you don't damage the nail matrix, the nail will continue to grow in that forward direction coming from the nail root area, okay, from the matrix part. So sometimes when people have ingrown toenails, because they keep getting them back, the doctor will destroy the nail matrix, hoping that that will cause the nail not to grow anymore. And then they would just have their nail bed, the epidermis underneath would be exposed. You wouldn't have the keratinocytes forming the shell of the nail, which gives us the protection. So they might be a little more sensitive there, but that's about it. Again, let me erase that so you can see your nail again. Voila. And moving right along, now we're going to talk about functions of your skin. So with functions of the skin, chemically, you have secretions. So if we are talking about acidic secretions, for example, we said that our sweat had a slightly acidic pH, right? And antibiotic things that we secrete would be, for example, sebum. Okay, so that is from our sebaceous glands. Remember, we said it was bactericidal. So this is kind of a review of some of the things we already talked about. Physical protection that our skin provides for us is it's an actual physical barrier. So it's dead cells at the surface, right? The apical surface are dead stratified squamous cells. We have our waterproof cell protection, right? And that protects us from trauma, invasion of buggies and whatnot, right? We don't want that getting in and infecting us. And also the whole waterproofing thing is really for us for dehydration. So it prevents us from dehydrating, okay? Biological things, that means biological meaning living things that give us protection of the skin are our dendritic cells and our macrophages. Both are phagocytic cells. Our dendritic cells are in the epidermis, and sometimes they're also in our dermis. And macrophages are in our dermis. They wander through the CT area. So both cells can wander a little bit and help find things that shouldn't be there. And hopefully we catch things with the dendritic cells in the epidermis first before they even get to the dermis. But that is that. Moving on to, that was protection functions. Now if we get into body temperature and regulation, with vasodilation, so when our body is too hot, the blood vessels will open up and it will bring the warmer or hotter blood from inside of our body to the cooler surface, kind of like a radiator, and that will help to cool us off. We also have sweat production to help cool us off, causing the water to evaporate from our surface, which takes the heat energy away. So this is part of what helps cool us off. With and when would we need to do vasodilation? When we're getting too hot, it might be because we were exercising, for example, or maybe we have an infection, we're running a fever, so we need to cool our bodies down. With vasoconstriction, we would do this when our bodies are cold. So we would constrict or narrow our blood vessels, keeping the blood in the warmer core of our body, and that process would help us to conserve our heat. So we can use vasodilation or vasoconstriction to regulate our body temperature, and this is part of what occurs with the more superficial blood vessels that are in our dermis or in the skin. With cutaneous sensation, that's getting information from our environment and sending that to our brain and telling our central nervous system what's going on out there. So these are sensory receptors. They're cutaneous, meaning in our skin. Vitamin D synthesis. So modified cholesterol in our epidermal cells. Our epidermal cells are also called keratinocytes. And so the modified cholesterol in the keratinocytes, when exposed to UV, will get converted to a vitamin D precursor. So that means it's the molecule before it becomes actual vitamin D that we use. So we can make our own vitamin D. The process starts in the skin. This gets modified in the liver and kidney, and we will get vitamin D, which is important for our bone formation. If we don't have vitamin D, we can't absorb calcium, and we need that calcium for the bone formation. So we do and should get out and get some sun exposure even in the wintertime so that we can make our own vitamin D. And if you can't, that's where people will do supplements trying to get enough vitamin D. Blood reservoir. Our skin is a blood reservoir. So we have lots of blood vessels in the skin, and constriction of those skin blood vessels would shunt the blood into the circulatory system. So what does that mean? It means that if we had some sort of an emergency, okay, and we need to say, oh, I don't need all this blood to go out to my superficial skin area. I need it for the core of the body to keep the heart pumping, to keep the organ systems moving, so it can pull blood from our reservoir of our skin, it constrict those blood vessels, pull the blood back in closer to the core to our circulatory system, and then it can be distributed to where it needs to, like keep it going to the brain, keep it going to the heart, that type of thing. What else can we do with our skin? Well, we can use it for secretion and absorption. So we secrete things like water and salt. So when you sweat, have you ever licked your skin or sweat got in your from your face got to your mouth, or you licked your lip and you're like, oh, that's kind of salty. So we can secrete water, we can secrete salts, secrete sweat, we secrete sebum. We talked about those guys already. And then there's something called urea. It's not the main function of skin. So very little urea will be secreted through our skin, but it can happen. And if you've ever seen somebody who was jaundiced, they are not processing their bile salts properly. It ends up getting out to the skin, and then their skin kind of looks a little more yellowish. So drink more water and make sure that their liver is functioning properly again, and they'll start to turn a more normal shade. As far as absorption, there is some absorption properties that can occur with your skin. And for example, we use one of those in a way to get some medications into people. So we call that a transdermal medication. They are usually giving you some sort of a fat-soluble prescription. So RX means prescription. What do I mean by that? Well, the fat-soluble, so it's moving something that can be absorbed, go through your phospholipid bilayer. So it slowly moves through the skin layers, getting to your blood vessels, so that it's a slow way of getting medication into your body, so it doesn't just get in too fast like if you took it as a pill or had an injection. And you could have it get absorbed through the skin slowly over time. And some people do not realize that this is real medication sometimes, and that putting on too many patches could kill you. But it uses the process of diffusion. So you have medication that's in a high concentration outside of the body in this transdermal patch that you stuck on the person's skin, and it moves from an area of high concentration to an area of low because there isn't any in the body, and that's how it diffuses through the skin layers. Okay? And we're done with chapter 6. Moving on to chapter 7 now. Bones. So a lot of this hopefully will be a review for you. And let's see, what do I want to tell you here? So after the end of this chapter, chapter 7, that'll be the end of exam 2 material with skeletal cartilages. So these are our bones come from a cartilage precursor, and we barely mentioned that when we were talking about cartilage before. What's the most common cartilage of our body? It is hyaline cartilage, right? So we said that we have a hyaline cartilage model. So the two types of cartilage that we have to do, that has to do with our skeletal system, is hyaline and fibrocartilage. Notice that I didn't mention or say elastic cartilage, because where do we find, the only place we find elastic cartilage? E for elastic, E for epiglottis, E for external ear. So that has nothing to do with our skeletal system. So that's why we're only talking about hyaline and fibrocartilage. So the basic structure and types and location. Your skeletal cartilages are mostly water. That's for resiliency or springiness. The cartilage is avascular and has no nerve supply, except one area, which we're going to call the perichondrium. Peri means around. Chondrium is the cartilage. And so this is containing the nutrients for the chondrocytes, or for the cartilage, and it kind of acts like a girdle. So men may or may not know what girdles are, but women definitely know what a girdle is. or not now, but your grandmas probably wore this stuff where they'd pull up a girdle, help suck in the stuff. So this helps keep things in an area, if you will. And when we say that it contains nutrients, what do I mean by nutrients? I mean it needs a blood supply going to that area, and there will be nerves near that area as well. And you're going to see how this looks momentarily. So talking about hyaline, which is our most common type of cartilage. And when we say where we find it, it'll be in articular areas. Articular means the lining of the joints. When we say costal areas, we're talking about ribs. When we say respiratory, we probably mean the bronchial rings, right? If we say laryngeal, you're going to see more in 228. There's all these cartilages. You actually have an eval on those cartilages in 228. And then nasal, some people think that their nose is elastic cartilage because it's springy, moves around, and kind of weird, but it is not. It is hyaline cartilage. So if nothing else, you can't remember what kind of cartilage it is, it's always hyaline cartilage. All right. Fibrocartilage. Many collagen fibers imparts a lot of strength, basically. So this is for preventing trauma between bones. So this was our intervertebral discs. These were the menisci of the knees, your two knees, and also the symphysis pubis. So we've kind of mentioned some of this before. This should be hopefully a good review for you. Growth can occur in two ways, and both ways that we talk about, appositional and interstitial, are due to chondroblasts. And the growth will stop when the cartilage is fully mature, because what do we say happens to cartilage once it's matured and it's done spewing all of its matrix out? It's been encased in its lacuna, right? So that's what we mean by fully mature. Now they're dormant and retired and just hanging out. So let's take a look at these two different ways that we do it. So a chondroblast, remember, was the immature chondro cell that produces the matrix, and a chondrocyte is the cartilage cell that is mature and encased in the, its own matrix that it spewed out, and that matrix again was made by the chondroblast. So keep practicing which word means what so you don't get confused. And when we say that the cartilage is fully matured, we're really talking about late adolescence for girls and closer to 18 to 21 for most guys. And let's look at the two ways that we can grow our cartilage. So appositional, think opposing sides, and interstitial, you want to think interstitial fluid, think between the cells. So in between is interstitial, opposing side is appositional. So appositional says it's growth from the outside via the perichondrium. We're talking about width here. So if I were to draw an area, let's say that these two lines are our perichondrium, okay? And lining that perichondrium will be these are cells, so I'm going to put little nuclei in it, and I'm going to put it on this side as well. All right, so here's the perichondrium. Here are the chondroblasts, because we're going to say that they are making matrix. And you can think of the perichondrium as like a wall. So the cell can't make matrix and push it this way. That wouldn't make sense. It only pushes it. So I'm going to erase that arrow because it doesn't go that direction. When it makes it, it can only spew it out towards the middle, okay? So both sides are doing this. This is appositional, so these are the cells that are lining and pushing the matrix in towards the center. So it's making this and pushing it in, okay? Now, the cells and chondroblasts that produce the matrix secrete medially, not to the perichondrium, but away from it or towards the middle. And this is what is making your perichondrium increase in width. If we talk about interstitial, so this is growth from within, what that means is if we have a chondrocyte here, okay, and it's sitting in, let's say, a lacuna, where do you think it's moving its matrix? It's producing the matrix and it's pushing it in all different directions, okay? And if this cell will fill that up until it's walled itself inside of its lacuna, right? And then it won't be, then it would be a mature cell, and then it's kind of locked in there. So these cells in the center are spewing its matrix all around. That's interstitial, and that would eventually increase the length of your cartilage, okay? So again, this was appositional, means that's a terrible arrow. Appositional means that you are spewing your matrix into the center. Interstitial means that you're spewing your matrix, you're in between, and you're spewing it all over the place, right? Okay, so that's our two ideas there. And if you wanted to, you could even put, to help you remember, another chondro, what do you guys think it is? Chondroblast. So let's say you had two of them. If it was spewing matrix here, it would end up pushing the two cells away from each other, and that would also increase your growth there as well. So there's no wall around the interstitial side of it, and they'll spew their matrix until they are encased in it. And so once it's encased, it's no longer a chondroblast, it's now a chondrocyte. Exactly, wonderful. So let's see, moving on to classifications of bones. You guys, this should all be review on classification now, because you guys have done all of this in lab. So 206 bones divided into two groups, axial skeleton and appendicular skeleton. So your axial skeleton is the skull, the vertebra, making up your vertebral column, your rib cage, and add in there also your sternum. The appendicular skeleton would be your upper and lower limbs plus the girdles that we'll talk about in a minute. Long bones are longer than they are wide. So it has a shaft and it has two ends. The shaft is called the diaphysis, which you'll see in a minute. So diaphysis, and the two ends are your epiphysis. So you have two epiphyses and one diaphysis, the shaft and the two ends. And most bones of the body are long bones. They were named for their shape, not their size. That's why we say they're longer than they are wide. So some examples of your long bones are, the obvious one would be like femur and humerus, but also radius and your ulna are long bones. And one that you may not have thought so much of until you did your bone lab, also phalanges, because these are long bones. They're longer than they are wide. Where are your phalanges? Hopefully you already know this. They were your fingers, right? And also down in the feet. Short bones are shaped somewhat like a cube. We don't have a whole lot of these. You're going to find these in the wrist and ankles. In the wrist, they're called your carpals. In the ankles, they're called your tarsals. If we're talking about a specific short bone, we have one called sesamoid bones. We do have a couple of them, but the main one that you guys know are the patella, correct? So the patella, sesamoid bones develop within a tendon, and these develop once the tendon experiences trauma. So if you guys looked at that fetal skeleton in lab, you may or may not have noticed, but it was a fetus, it hadn't been born yet, and even if it was a newly born baby that had perished, if it wasn't crawling yet or putting any pressure on the knee area, then it would not have a patella. Once it did, you'd have a cartilaginous area that would start to then, as trauma occurred, end up forming its bone, or the sesamoid bone, or the patella. And think about it. Did the baby need a patella while it was still in the womb? No, it's not going anywhere, so no trauma was occurring. Flat bones. These are thin, flat, and possibly slightly curved, it says. Great examples of your flat bones are your sternum, your scapula. Those kind of should seem, at least the scapula should seem pretty obvious. Most of your skull bones are, and then also your ribs are considered flat bones. The facial bones are not considered flat bones. So when we say skull bones, we're talking about the cranial bones, okay? And let's see, irregular bones. These basically are anything that did not fit in the above categories. They're not long, they're not short, they weren't flat, they're irregular. And so the vertebra are your pretty obvious irregular shaped bone. They don't look like anything else. And you have facial bones would come into this part. So your maxilla, your ethmoid bone, things like that, and then hip. And I hope you guys realize that hip is called your os coxa bone, correct? If we look at the functions of the bones, so support seems pretty obvious, basic framework of the body. Protection, this seems fairly obvious to me. This is the armor for important soft tissue things. So your skull protects your brain, the vertebra protects your spinal cord, the ribs protect your lungs and some of your internal organs and your heart and so on and so forth. So protection seems pretty obvious. Movement. So our muscles will use our bones as levers. So now that you guys are just barely going to start to get into muscles after you did your bone eval this week, and going into the next couple weeks, you guys hopefully will start to realize that when the muscle contracts, it moves the bone, which is a lever, thus the movement part of function of bones. Also, it is a storage area for mineral and fat. So this is a reservoir for calcium, phosphate, and adipose. And adipose, you're going to see is going to be stored in the diaphysis or shaft of it. This is where you have fat, and you're going to call it your yellow marrow, which we'll talk about in a moment. And some people eat bone marrow. My grandma loved sucking the marrow out of the bone that she would eat. And I haven't really tried it. I probably should try it now that I'm an adult and have branched out and not so afraid to try things, right? There's also blood cell formation with our bones. So we call this hematopoiesis. And so blood formation, so our blood cells only live about 120 days. And all of our blood cells originate from the bone marrow, which I just told you was in the diaphysis. We have bone marrow in the diaphysis. And so bone marrow, we are going to get our red blood cells, our white blood cells, and our platelets are all made from our bone marrow. If we look at bone structure, now we're talking about gross anatomy. So we have bone textures. You can have compact bone, and we can have spongy bone. So compact bone is the smooth, dense outer layer that we end up seeing on the bone, and we also call that the surface of the bone. So this is hard bone, and it forms the outer shell of all bones. And if we look at spongy bone, it has another name, trabecular bone, and sometimes you might even hear people call it cancellous bone. So spongy bone or trabecular bone is internal to the compact bone. It tends to have a honeycomb shape or appearance formed by small, flat pieces of bone called trabecula. That's why they have the other name, trabecular bone. It contains red or yellow marrow depending on the age of the specimen. So I'm going to draw you a typical structure of the typical long bone. And if you hear Sherry talk about it, she likes to call it the Bam Bam bone. So let's see. So our first area, don't laugh at my drawing. Okay. And this area here would be called the diaphysis. And this area here would be the one epiphysis. And here's your other epiphysis, because we said epiphyses are at the two ends. Diaphysis is the shaft or the center area of your bone. Now, we also have, I'm going to draw this here first. Okay. And I should have drawn that in another color. Let me do that real quick. Trying to make the same colors for you guys so you associate the same thing. So if I draw a blue line in here and a blue line in here, and I'm also going to tell you that I'm going to line the outer part of my bone here with blue, and I'm going to line the outer part of my bone there. This is the articular surface, and what did we say the articular surface is covered by? Do you guys remember? Let me give you a hint. Starts with an H. If you know nothing else, it's hyaline cartilage. So I'm going to put H at the two ends here because our articular surface is lined by hyaline cartilage. Now, that other blue area that I drew is going to also be hyaline cartilage here first. When you are young and not fully developed. And so that is first going to make your epiphyseal plate. Later, when you're done growing, and it's going to end up becoming your epiphyseal line. Okay, but for now, we're just going to call it the epiphyseal plate. We have hyaline cartilage there. Let's draw in the center. We're going to have an area there called the medullary cavity, and I did it with yellow because I want you to associate it with our yellow marrow. So the medullary cavity implies an open space, right? And that's going to have our yellow marrow in that area. Now, real quickly, remember we said the outer shell of our bone was what kind of bone? Compact bone. So this is compact bone here. All right. And we are going to surround this area with something called, let's do this in green. So if I have this covered by something that surrounds our bone, what kind of name do you think we should give that? How about periosteum? So peri, around, osteum means bone. So we are also going to have something here, a whole bunch of fibers. And those are going to be what we'll call Sharpie's fibers. And we'll talk about those guys again in a little bit. And they're on both sides all the way along. I just was drawing a few of them for you. So that's connecting your periosteum and tacking it onto the compact bone part of your long bone here. We also will have, let's see, let's do red, why not? We'll have an area in the epiphysis here on both sides, and this is where we'll find our spongy bone, okay? So this will be where we might have red and or yellow bone marrow depending on the age of somebody, and it's where we find the trabecular, so it has a trabecular pattern to it. What else do I want to tell you here? Oh, our perichondrium also surrounds, I should say, over that. Is it over the hyaline surface? Let me double check before I tell you wrong. Yeah, let's put that across here too, surrounding the whole area with our perichondrium, sorry, because we're over the chondro, the hyaline cartilage part, right? Perichondrium will be over the cartilage here. Periosteum is over the bony area there. And do I need to tell you anything else? No, I think that's pretty good. So again, you guys can come back and try to draw things and remember where the epiphysis is, the diaphysis is, where do you find your medullary cavity, where are you finding periosteum, where are you finding perichondrium, where is your hyaline cartilage, where is your epiphyseal plate or line, and you guys can redraw something like this on your exam and remind yourselves where you find all of those things. So I hope that is helpful. And what else do I want to tell you? I think that was good. All right, moving right along. Let's see. And here they have a picture for you. And I wanted to tell you that those perforating fibers, so if this is our periosteum and they flapped it back there, so you have all these little fibers tacked on to the surface or the compact surface of the bone, those perforating fibers are the same thing as Sharpie's fibers. Sharpie's fibers, okay? So I just wanted to note that real quick there. And I don't want you guys to worry about metaphysis. Don't worry about that. Just talk about the diaphysis and the epiphysis. This is saying distal, this is saying proximal. You guys should know distal and proximal from your bone labs. And articular cartilage, what did we say that's made out of? We said it's always hyaline cartilage. That's at both ends. And you guys know that spongy bone, another name for that, and you knew that that was at the proximal area of your epiphysis, and trabecular bone, right? And here is an epiphyseal line. So is this an adult or a child if it's an epiphyseal line? Line means adult. And we had our compact bone on the outside. And let's see, here's your medullary cavity containing the yellow bone marrow. So that's going to be in this part of your bone. And what else do I want to tell you? This picture here is pretty helpful. Let's see. So remember, blast means build bone, clast means to break down bone. So an osteoblast is building bone. The osteoclast is what is going to be breaking down bone, which means another name for that would be reabsorbing bone. So when you need to pull minerals and utilize stuff, you can break it down. When you're ready to build it back up, the osteoclast will be doing more of that activity. And then, so blast is for growing, clast is older and breaking down. And when you have more osteoclast activity than blast activity, meaning you are breaking down faster than you're building it, that's when you have things like osteoporosis, which we'll talk about at the very end of this chapter. So if we go through the terminology here, diaphysis or shaft is mostly compact bone with a hollow center called the medullary cavity. Medullary was central, right? Contains yellow marrow, which we said is adipose. The epiphysis, the two ends, so you have the knobby ends, mostly spongy bone with a thin layer of compact bone covering it because it covers the whole area. The epiphyseal line means it's the junction between the epiphysis and the diaphysis in an adult bone because it's an epiphyseal plate if it were a child, right? Let's see, where else are we? Periosteum is protects and nourishes the bone. There's two layers. So the periosteum is an anchor point for tendons and ligaments, and it's anchored to the bone by perforating fibers, also called Sharpie's fibers. And it is made of, these perforating fibers are made of collagen, which is really strong. So for collagen, geez, I can spell today. So one thing that I want to mention here is, so for example, we are saying that this is an anchor point for these ligaments and tendons. If you are somebody that didn't prep and you just decide you're going to start exercising one day, go full out and do it, you start running down around the lake or something like that, and then later you have all this pain because you have something called shin splints, let's say, right? Because of all this new activity you did all of a sudden, you didn't slowly work into it. So all of a sudden, your tendons and ligaments are tugging on this periosteal layer and tugging on these collagen fibers or these Sharpie's fibers, and you are ripping them. And because you did too much exercise too quickly, now it needs time to repair it. So once it repairs, you won't hurt so bad and you'll be able to go back out and hopefully slowly work into your exercise routine and not go crazy and all at once, right? So there's many blood vessels and nerves. It's dense, irregular connective tissue woven into, nerves are woven in with the blood supply. What else do I want to tell you? Nutrients for the bones. So blood has to go to the lungs, and the gut to get its nutrients and oxygen. So the blood vessels go to feed the bone and remove the waste. So that's why it's in the periosteum surrounding the bone, and will get information and nutrients to us. And moving on, we have the fibrous layer and the osteogenic layer. Fibrous layer is the outer layer with dense, irregular connective tissue, where I said we have many blood vessels and nerves. The osteogenic layer is lined with osteoblasts and osteoclasts. But there are more osteoblasts here than clasts. It's connected to the bone by those perforating fibers. So which layer would be closest to the bone surface? Since we said it's lined, we're going to say it's the osteogenic layer, okay? Endosteum is another layer that we can talk about. So this lines the medullary cavity. Medullary. So before we were talking about outer, now we're talking about a more inner area of the bone. So this contains osteoblasts and clasts. And in this case, the osteoclasts, all right, there are more osteoclasts than blasts. If we're talking about our articular cartilage, this is a thin layer of hyaline cartilage overlying the epiphysis, those outer areas. So this is the great shock absorber that we have, and also reduces friction of the bones at the joints. So that's why it's at the ends of the bone, right? And the perichondrium is only at the exposed surface. So when we drew our picture up here and I said perichondrium is out on the outside of the articular surface, which we drew in blue for our hyaline cartilage, and that was our only exposed surface. So perichondrium. So as you guys are learning terminology, go back and look at those pictures again and put those words to that picture. If we look at the structure of short, irregular, and flat bones. So this is compact shell with a spongy area sandwiched between the bones. That spongy area we call diploe, and that's our special name for that spongy bone. And I know it looks like a funky little word, but diploe. And we also have a periosteum. We also have an endosteum, endo within, peri around. But there is no medullary cavity with short, irregular, flat bones, okay? And moving right along, now we get to talk about our red bone marrow. So it's showing you one of the cranial bones, which we said was a short, irregular, flat bone. So red bone marrow and yellow bone marrow. Let's talk about red first. So it says hematopoietic or blood cell forming. So the red bone marrow is where we have hematopoiesis occurring. So this is where our red blood cells, white blood cells, and platelets come from. So if I misspoke earlier in the notes, go by what I'm saying right now. I apologize. And the location of red bone marrow is going to be found with newborn and children. It's going to be in all the spongy bones and the medullary cavities in newborns and children. So all the spongy bones, that also includes our diploe, okay, for kids, newborns and kids. But in an adult, okay, mostly in the diploe of flat bones, okay, so that's where we're talking about our skull bones, right, cranial bones, but also in the proximal epiphysis of some of our long bones like the femur and the humerus, okay? So you may find this in the hip bone, the sternum, and the skull bones. And that's why I said just the proximal area of the humerus in that above picture would have the this area here. So it's not down here because in this long bone it doesn't have spongy bone down there. So I just wanted to point that out real quick.
I don't know what you mean by I hear so it's not down here because in this long.
Don't you love Siri when you're trying to talk? I don't know why it activated. All right, so moving right along, if we are talking about yellow bone marrow, this is fatty or adipose, and then it becomes fatty adipose CT. The location would be found in medullary cavities of adult long bones. So not in the little kiddos here, but our adults. It extends into the spongy bone of most long bones. If we're looking at the microscopic anatomy or bone connective tissue, right? So cells of the bones, we have osteoblasts. Remember, blast means to build. So osteoblasts are found on bone surfaces. They're not encased in the bony matrix. And the osteoblasts secrete something called osteoid. And this is actually a precursor. And this is the non-calcified bone matrix. Matrix is the ground substance plus all the fibers. So osteoblasts are making osteoid. That's what they are secreting and making. Osteocytes are the more mature cells, right? So previous osteoblasts that are now surrounded by bony matrix became an osteocyte. Because it's mature, it's no longer producing osteoid, and we find these in the lacunas, the lakes, or the little what do we call that? The little site for them to hang out in, right? If we are talking about osteoclasts, so these are large multinuclear phagocytic cells. We find these on the bony surface and the pits, and they will break down bone. So clast you can think of as, let's see, it's breaking down. So come up with your own mnemonic for how a clast is going to break it down, right? And this allows you to reabsorb that area of the bone so that you can pull out some of the calcium or phosphorus or something like that, minerals from there, utilize it, and then you can later rebuild it with osteoblasts. osteoblasts that are found on the bony surface as well. So these guys are all working at different times. An osteoblast later can become an osteocyte once it's surrounded itself, but then an osteoclast will break things down. And now let's talk about compact bone. So we have a what's called the Haversian system, or an osteon, and that's what you end up seeing. So the whole thing, like it's saying, that whole set of circular area was the osteon. You have lacuna, which are all these little lakes in here that have osteocytes, because site was mature. It's encased itself in there, and now it's done. You have your central canal, which is, I should do a whole different color here so you can actually see it on the black. Let's do red. So this area here is your central canal. What do we find in our central canal? Oh, look, blood vessels and also nerves. And you have concentric lamellae. So we can draw that in blue. So a lamellae is going to go all the way around, and then it's like the rings of the tree, right? Those are lamellae. And what else do I want to tell you? So in a Haversian system, or osteon, the whole thing is elongated cylinder that runs longitudinally. You can see this under the microscope, so this should already be drawn out in your histology. The lamella, we said, are the growth rings, so just like a tree. We also have something called perforating canals, or Volkmann's canals, so you should know both names. They run at right angles to the osteon. So I'm going to draw that in red. So for example, this could be a central canal, this could be a central canal, and then a perforating or Volkmann's canal might be connecting the two central canals, okay? So they tend to run horizontally or slightly vertical, so you might also see two central canals and a Volkmann's canal looking kind of like an H. And then you might have another Volkmann's canal connecting it to another central canal over there. So this is a connection system. In this picture here, you don't see a Volkmann's or you don't see a Volkmann's or perforating canal in this particular picture. And that's why we wanted you guys to see a longitudinal picture where you could pick out the difference between a Volkmann's canal or a Haversian canal. So you should know all those AKAs, central and Haversian, perforating and Volkmann's. And you'll notice that the Volkmann's canals tend to also be shorter, not as long as your Haversian or central canal. Let's see, what else can I tell you? The lacuna, so this is when it was in cartilage and bone, we had lacunae, and these were spaces that housed these spider-shaped, now that we're talking about bone, we're going to say osteocytes. You have canaliculi, which connect the lacuna to each other. So that's why they're showing you on the canaliculi would connect, here's a lacuna, and that would be a canaliculi. Here's a lacuna and a lacuna, here's a canaliculi, connecting the two of them, okay? And I'm going to erase all that extra drawing I put on there so that you guys can see your picture a little better. There we go. All right, and now moving on to spongy bone. So that was all for compact bone. Now we're talking about spongy bone. So we have trabecula, open lattice of narrow rods and plates of bones. So there are no osteons with this, but we do have a lamellar pattern within the plates, and it's a bony meshwork that's pretty strong. So you could think of this kind of like a jungle gym or like a house of cards. So if you had a structure like this and stacking it again, and then you can stack it again, and it would be pretty strong, and you could stack again if you wanted to, but that's what you're looking at when you're saying trabecular or spongy bone. That's the lattice work that can bear weight of many kinds. And let's see, further away from the central canal means that you would have less nutrients. And so you can only grow so fast. Let's see, if we're looking at, this picture was showing you a lacuna and the branching out, so it had an osteocyte within the lacuna, and the canaliculi would connect this osteocyte to another osteocyte that's also in another lacuna, okay? So you could think of that. You have your concentric lamella, so these are your tree rings. So you had one tree ring, then another tree ring, so one tree ring, then another tree ring, then another one that grew. I'm going to erase that so you can see that better without me putting all my crazy drawings around it. All right, and what else do I want to tell you? Let's see. This is that trabecula look of the spongy bone. Can you see how real lacy it ends up looking? So you can kind of think of it like stacked up like that. And I want to tell you anything else. No, let's move on. So the chemical composition of bone, if we come down here. So it's made out of both organic and inorganic parts. If we talk about the organic parts, that only makes up about 35%. When we say organic, that's the living part of the bone. When we say inorganic, that's the non-living material. So what would make up the organic parts? So if we're talking about cells, this is a combination of our osteoblasts, our osteoclasts, and our osteocytes. Those are all make up part of the organic part. And then, of course, osteoblasts are what make the osteoid, or the collagen fibers and ground substance. Collagen fibers and ground substance. And we said that's made by the osteoblasts. Okay. If we're talking about the inorganic parts, that's the 65% of the composition of our bone, and that would be non-living material. That's the calcium salts, meaning the phosphates and carbonate, and this is what gives the hardness to your bone. So I want to bring you attention over here where it says the combination of organic and inorganic is what allows for the strength of our bone. And when we're looking at that, it says if we had 25,000 pounds per square inch of compression going on, and then we can also withstand 15,000 pounds per square inch of tension. And so what I want you guys to think of compression is that if you had a whole inch of compact bone, that would withstand 25,000 pounds per square inch of compression. But none of our compact bones are a whole square inch like that. They're really only 1 to 2 millimeters. So it's saying that if it were a whole square inch, thus the PSI part, it could withstand that much. When it says the 15,000 per square inch of tension, think of that as like pulling. Okay, so pulling up on your bones, basically. So that's a lot of pressure, a lot of tension that you can withstand because of the inorganic and organic composition of our bones. So I thought that was pretty cool. If we're looking at the nutrient requirements of our bones, you're talking about we need vitamin C and D, and we also need calcium. So vitamin C is needed for the collagen formation. Vitamin D is needed for calcium absorption. So you can't get calcium into your bones if you don't have vitamin D. So that's why you need all of that. Vitamin C and D, and then obviously calcium as well. Let's see. And in order to get your vitamin D, you need sunlight for that. If we're looking at bone formation, or another word for that would be development, that's where we're talking about osteogenesis or ossification. Osteogenesis, osteobone, genesis means create or from like scratch. So this is bony formation or ossification. And the formation of the bony skeleton starts at about, I don't know if your guys' notes was incorrect or not, it should say 8 weeks. Okay, so it starts at about 8 weeks. The old notes used to say 6. And so 8 weeks of gestation. And that means you are still within the womb, okay? So that means you're in your first trimester still. And bone is formed one of 2 ways. So we have 2 types of ossification. It can either be intramembranous or endochondral formation. So intramembranous, in between membranes, is essentially what that means. So that's why it says forms within a fibrous membrane. And we're talking about dense, irregular CT, okay? These would be our cranial bones of the skull, and the clavicles will form using this process. So if we look at the picture below, it's saying that ossification centers form within the thickened regions of the mesenchyme first. And so here you have your osteoblasts that are producing osteoid. okay? And that's where your first ossification center is going to occur. Then the osteoid undergoes calcification. So remember, these guys, let's see, so once it gets slightly mature and it gets encased and it is no longer producing osteoid, that's when they're going to be called an osteocyte, because that's the mature one. So you may still have an osteoblast here producing osteoid and making matrix, but in here we're now ossifying. Then it says woven bone and surrounding periosteum form. So remember, periosteum will give you that wall so that you're not going to be producing this direction. You're only going to be producing in that direction, is what it's saying. Lamellar bone replaces the woven bone as compact and spongy bone form. And so what do I want to tell you here? Let me go back to my notes real quick. So if you go back and use some of the terminology we learned at the beginning of this lecture, then these cells here are doing appositional or interstitial. Appositional. So I'm going to put an A there to remind you this is appositional, because remember, it's not producing it back this way, it's spewing it this way. These guys, before they became osteocytes, they were doing interstitial. Okay, so depending on where it is and how it's spewing, in this case it's osteoid, would be interstitial or appositional growth. And let's see, at the end, I just wanted to say that this is the compact bone, the outer hard shell. And in here, this is all spongy bone. That's why it's showing you here, and that's why it looks spongy. It's got the holes in them and stuff. And then you had your periosteum along there. So if we're looking at the other kind of growth, we have endochondral. So this is bone forms within a hyaline cartilage model. And didn't we say this is where most of it is forming from? So I wrote it kind of out on the side here so that it would be hopefully more helpful for you. Let's see, what else do I want to tell you? All right, so with endochondral, bone forms within a hyaline cartilage model, inside cartilage, endo within chondral cartilage. So it could have been called endomembranous ossification, but they like intramembranous, but we want to call it endochondral. So the chondroblasts in the perichondrium convert to osteoblasts, and the osteoblasts then invade the cartilage model and form ossification centers. So we basically are going to have two ossification centers. The primary ossification center is in the diaphysis only. So it means that primary ossification is going to start in the diaphysis, whereas secondary, so I'll put a little primary there, whereas the two secondary areas would be in each epiphysis. So we have two secondary ossification centers. So primary ossification will happen first, then we will get the secondary ossification centers happening second. So now let me give you the story of it. So formation of the bone collar is going to occur first. So this is this part here. At the primary ossification center, where the chondroblasts are in the perichondrium convert into osteoblasts in the diaphysis. This creates the bone collar. This gets ossified, but the problem is now how do we get nutrients there? Well, we can't get nutrients into this area once we've ossified it, so the cells end up dying. Those deteriorating cartilaginous matrix in that area happens, but because it's living tissue, we don't want decay. So blood vessels end up sniffing out this decay that was starting to occur in here and will then infiltrate and help clean things up. So macrophages come in and we'll break it down and we can utilize things. So we clean up the debris in here. We have a good vascular supply now, which means healing can occur, and blood vessels come from the periosteal area. It invades and vascularizes this area. Now you have osteoblasts that can follow the trail of the blood vessels created. So you've essentially, the chondroblasts are in the perichondrium, then they become, let me make sure I'm reading it properly for you. So the chondroblasts in the perichondrium, or the periphery of the midsection, convert to osteoblasts, forming your bone collar. So that's that part. Then the osteoblasts invade the cartilage model and form ossification centers. So you have your primary ossification center in the diaphysis that's first occurring. The blood vessels invade the deteriorating center. Then the osteoblasts will follow and invade into that cartilage model and form an ossification center, forming That's what we're talking about all right in here with the primary ossification center. So I just wanted to point that out. I kind of said it twice to you guys. I hope that helps a little bit. Replay it again, think it through. Let's look down here. It says fetal hyaline cartilage model develops. So yes, we knew that happened. Then the periosteal bone collar forms around the diaphysis. That was this part right here. Then we have our primary ossification center in the center of the diaphysis. That happened in here, so that was perfect. Then we got our secondary ossification, I can't talk today, secondary ossification centers within each epiphysis. So you're going to end up now with a secondary and a secondary occurring. And then bone replaces almost all of the cartilage except the articular cartilage at the ends and the epiphyseal plates. That stays as hyaline cartilage until later when they're what's called postnatal bone growth, or when you're done with the growth of length. So when you are now becoming more mature, the epiphyseal plate then becomes your epiphyseal line. So let's talk about how that happens. So postnatal bone growth. So you've been born, now we're growing more. This would then stop typically, give or take, around the age of 21. I'll modify that in just a second. So growth in length. So primary and secondary ossification centers grow toward each other. So it's with the primary, you've got it growing this way and this way, right? Here's your epiphyseal plate. Here's your, so diaphysis here, epiphysis, you're going to get secondary, here's your primary area, okay? So lengthwise growth continues until the epiphyseal plate is consumed. Then the epiphyseal plate is very active on the diaphyseal side. So which side is the diaphyseal side of this? This is the diaphyseal side, right? The side towards the diaphysis is what it's saying is being very active. So the epiphyseal plate closure occurs at about age 18 in females and about age 21 in males, give or take. So that means bones stop growing longitudinally, which was, again, interstitial growth, right? Then growth in width and thickness. So here we're talking about osteoblasts in the periosteum continue to lay down bone. So these are the appositional type growth. And at the same time, the osteoclasts start destroying bone from the medullary side. Remember, medullary side is, we have our medullary cavity in here, right? And remember the secondary ossification centers are at each epiphysis. Oh my goodness. Thank goodness we're done here almost. Let's talk about bone homeostasis. Okay, you guys know that bone homeostasis means that this is not normal, right? So what we're saying here is, sorry, scratch what I just had you. We're not just done yet. Oh my goodness. Bone homeostasis. This means what we should be doing on a normal basis to keep the bone healthy, to keep our body healthy. And we do this through remodel and repair. Okay? And let's see, I need more caffeine apparently. Maybe I can talk better now. Bone homeostasis. So we're doing this all this time. Remodeling means the growing of bone. Repairing means like if you had a fracture, you got to fix something that happened. So with remodeling, as you're growing, bone deposition is occurring. That's done by the osteoblasts, and bone reabsorption is occurring, resorption, and that's done by osteoclasts. So almost 20% of the adult skeleton is replaced yearly. So this is because of that organic nature of our bone. When we need calcium, when we don't need it. So replacement rates will vary depending upon your location. So again, not only location dependent, but also different types of bone between spongy and trabecular bone might make a difference on how you're remodeling also. Spongy bone is replaced more frequently. Compact bone is replaced at a slower rate. We also have things like hormonal control. So this is needed for normal bone. Lots of hormones are involved. So let's look at the different hormones involved in this process. So with growth hormone, that is directly stimulating growth of the epiphyseal plate. Okay, so another, you'll see us, so I'm going to circle epiphyseal plate. Growth hormone is oftentimes abbreviated GH. We also have thyroid hormone, which is TH. That is, it works with growth hormone to stimulate the growth activity at the epiphyseal plate. So we need that also. So inactivity or hypothyroidism would affect the linear growth of your bone. We also have sex hormones. So these stimulate aggressive bone growth in areas of epiphyseal plate. So estrogen has a stronger effect of taking over the epiphyseal plate or line. And what that means is women stop growing sooner than men. So you'll see girls might stop growing in their height and stuff, say maybe around 16 to 18 years old. And then you see like a guy when he was 18, and then you might see him again when he's 25, and you're like, holy moly, the guy got bigger. Okay, so that's why. Then PTH is parathyroid hormone. That stimulates osteoclast activity, which is important in regulating your blood calcium levels. So it's released by parathyroid gland when the blood calcium levels are low. Now, I want to point out to you guys, blood calcium means the calcium level in your blood, not in the bone. So basically, increasing blood calcium levels due to bone resorption means that the parathyroid hormone is stimulated by blood calcium levels. Increased parathyroid hormone would mean that you would get more blood calcium levels. So if blood calcium was low, parathyroid hormone will increase so that the osteoclast activity will increase, so increased blood calcium. Once blood calcium increases, then the parathyroid hormone can then decrease because it says, oh, you have enough out here. So this is classic negative feedback. And if you have low calcium in your diet, your bones will be weak because you're going to start pulling it from your bones because it's not in your blood. All right, so I just wanted to point that out a little bit. Calcitonin. So I remember there was like a mnemonic, calcitonin builds more bone. So this says it inhibits osteoclast activity in children, so it will decrease blood calcium. So what do we mean by this? So we don't have a lot of this in humans that we talk about much. Usually you need high doses of it. So high doses would increase bone density. It would increase osteoblast activity. So high doses of, what do I want to tell you? They used to use this as a treatment. I don't think it was very effective. So if you have, let's just move on. I wouldn't worry too much about calcitonin, just decreases blood calcium. There you go. Let's talk about vitamin D. It is produced, the production of vitamin D we already talked about starts in the skin. Then it goes to the liver to get modified. Then it would go to the kidney to get modified. And what we're talking about there is modification, and after that final modification, so we need calcium absorption from the gut. So if you don't get enough vitamin D from being out in the sun, then you're going to end up supplementing it in your diet by taking supplements. If we look at mechanical stress on bones, so this is due to muscle pulling and gravity, so compression and tension, stretch forces. So what we want to talk about here is no matter the person's age, we want to keep osteoblasts happy, right? So weight bearing and weight training would increase your bone density, all right? So what they mean is if you're swimming in a swimming pool, you're buoyant, you don't have gravity forces on your body like normal. So if that was your only form of exercise and you were osteoporotic, you're not helping your problem. You need weight bearing, meaning gravity needs to be pushing on your spine. You need to be walking above ground is one of the best exercises they could do. Running would also help as well. But if they're older and they don't like running, that's fine. So that's what we're talking about on mechanical stresses. Let's see. Repair of fractures. This is exciting, right? There are 4 phases in bone repair. So first, you ended up breaking your bone. Right? So you break the bone and a hematoma forms. So you have torn blood vessels of the bone, and the periosteum causes a hemorrhage. A hemorrhage means that blood is filling and causing swelling of the area, and you have a clot. So that's why they're showing broken bone, blood is leaking out, causing the hematoma there. So your body says, oh, we need to fix this. So it's going to form what's called a fibrocartilage callus as your next phase. The fibrocartilage callus, this is regenerating capillaries, move into the hematoma area. So you have this blood vessel, right? And he's going to come in and they're going to spread out so that they can start to do their work. So macrophages are in the capillaries. They are going to invade this area and start cleaning up the debris, meaning chewing up the stuff that doesn't need to be there and start getting rid of that. Fibroblasts, then lay down collagen. Oh, fibers, right? Fibroblasts make collagen and stuff, and some will convert to a chondroblast. So your fibroblasts can become different cells sometimes, and this ends up putting on like a soft splint. So this here is now a fibrocartilage splint, essentially. That's your callus there. Then you're going to form a bony callus. So this is phase 3. So osteoblasts and osteoclasts now migrate into the fibrocartilage callus. They will begin ossification and formation of the spongy bone. So here's that trabecular look. Here's your spongy bone. It formed it out there too. Okay, and then the last phase is going to be bone remodeling. And this is where that large bulging callus ends up getting remodeled in response to mechanical stimuli. So then you can finish forming your compact bone on the outside and the spongy bone on the inside there, right? So what else do I want to tell you about bone remodeling? Let's see. So with the hematoma, you had a blood clot. You needed to get rid of that. So that's why we needed to get the macrophages in there and get rid of it in the fibrocartilage callus. Let's see. The fibrocartilage callus is going to help with shock absorption. That's why it's a good splint. With the bony callus, we're talking about scar tissue, broken ends of the bone. You can see this part now in the x-ray when you take an x-ray of it. And if somebody's wearing a cast, their muscles in the area around this is going to be kind of puny looking, especially when they remove the cast. One arm is not going to look like the other arm, or one leg won't look like the other leg, because if you don't use it, you lose it, right? And you're not supposed to be doing too much when you have that cast on. With the bone remodeling, that mechanical stimuli, you could think of it as like mechanical stress a little bit, right? So using it as you start to move around on it more is going to help this. Sometimes if people aren't healing, they'll give them a bone stimulator. And so they found that people that actually with the cast on who were still walking around and banged the heel of their foot, let's say, it put a little bit of a stress on the bone and caused the osteoblast activity to increase and heal faster and better. So that's why they started implementing bone stimulators for those that couldn't get that to happen. And so it puts like a little vibration in there, causing that little bit of mechanical stress to help. And who would heal faster, kids or older people? What do you think? Pretty obvious. Kids seem to heal really fast on everything, right? So now let's talk about homeostatic imbalance, the word I was trying to say, unfortunately, before. I didn't mean to confuse you guys. So homeostatic imbalance means that something isn't right, correct? This is improper condition of the bone. So the only two we're going to talk about are osteomalacia and osteoporosis. In osteomalacia, this is another way of saying soft bones, or the bones are not mineralized properly. That's the key there, the mineral. So bones can bend or fracture more easily because of even your own body weight. You need proper mineralization to have the right hardness of your bone. And so if you don't have the right minerals there, it becomes soft. So bones soften and can bend or fracture more easily. A similar condition in children would be called rickets, where they have the bowing of the legs. So in adults, it's osteomalacia. In kids, it's called rickets. And it's usually a calcium and or vitamin D deficiency, because that's part of needed for our mineralization. So in order for calcium to be absorbed in our bloodstream from our diet, we need adequate vitamin D levels. So if you don't have proper vitamin D, that's why you won't have proper calcification. So the treatment for this would be to give calcium and or vitamin D supplements. That makes sense, right? Or get it in their diet. So also you'll notice that your dairy products oftentimes are fortified, meaning that they have added vitamin D and or calcium to it, because they know it goes hand in hand. We don't see this kind of problem typically in our society. People typically are getting enough vitamin D and calcium, but not always. And you would see this maybe in other societies. As far as osteoporosis, this is where endosteal bone destruction is faster than periosteal bone deposition. Okay, so what are we saying here? The osteoclasts are outpacing or working better or faster than the osteoblasts. So we're breaking down bone faster than we're building our bone. Thus the bones end up looking more porous or lighter. And you guys remember hanging on to that pelvis in the bone lab? And one of them was much lighter than the other pelvi that were there, right? So the bones, so would the bone have normal composition? Yes, the mineralization is fine. It's just the bone is breaking down faster than it was being maintained or built. Okay, so this is not a mineralization problem. All right, but it's a reduced bone mass, but the chemical composition is normal. And with the circle means normal. Prevention is the key. So while you're growing up and even during adulthood, you want to have proper calcium and vitamin D levels. You want to get exercise. Weight-bearing exercise is the key there. Avoiding things like carbonated beverages, alcohol, and smoking. And you're going, well, what's the big deal with that, right? Well, for one, let me see, where did I write this? I want to make sure I say it right and not mix it up. So carbonated beverages leach calcium from your bones. So then you're not going to have enough calcium to be able to have the right mineralization in that case. Alcohol and smoking both slow down osteoblast activity. So if you're slowing down osteoblasts, then you're making it even easier for the osteoclast to be doing their thing. So you're not helping things. That's why carbonated beverages, alcohol, and smoking would be things to avoid. You need to maintain your normal hormone levels. So for example, let's see, where do I want to tell? Women need estrogen. And so when they hit menopause, they have less estrogen. Thus, this is why you will see more women once they're getting menopausal starting to have osteoporotic type symptoms. And men, they need testosterone, but guess what? Testosterone levels stay the same. So they don't, unless something else is going on. So as long as they have normal testosterone levels, they don't get a big decrease of that normally in their life. So there you go. And prevention is the key. So when you're young and growing, play outside, jump up and down, play outside in the sun, have proper calcium in your diet, walk a lot, that kind of thing. Maintain normal hormone levels. Some prescriptions can slow down the osteoclast activity, and all it is doing is trying to give your osteoblast time to catch up. And so you still need to supplement with calcium. So that was the end of all the material for exam 2. I'm sorry if we went over in time. Good luck studying, and you guys can ask questions when we come back on Tuesday, or you can email or post in the forums. Have a great weekend, guys. Bye-bye.